Hi everyone, and welcome to section 9.3, which is similar to the other sections in that we're talking about hypothesis testing for a population mean, but the difference between this section and the other previous, I think it was 9.2 or 9.1, is that the standard deviation is not known in this case. Previously, we were talking about using a hypothesis test when the standard deviation is known. So we're going to use the two methods, p-value and then critical value. I am happy to announce I'm going to skip the table part and just go ahead and use the calculator part and show you how to do this on the calculator, okay? If you're dying to know about how to use the p-value method with a table, you can go ahead and visit me in my office hours, same link, Fridays at 12, and I can show you then. Okay, so let's go ahead and start with an example. We have here that in a recent medical study, 76 subjects were placed on a low-fat diet. So 76, that's important. After 12 months, the sample mean weight loss was x is equal to 2.2 with a sample standard deviation of xs is 6.1 kilograms. Can we conclude that the mean weight loss is greater than 0? So that's kind of like telling us, that's the, alternative hypothesis here. So if we knew the population standard deviation, we'd be able to use the z-score, but we do not, okay? So what we do instead is we use t-scores, the t test statistic, and we use this formula here, S instead of the sigma, because it's sample standard deviation. So under the assumption that the null hypothesis is true, the t-statistic has a student's t-distribution with n-1 degrees of freedom. So degrees of freedom is n-1, where n is the sample size. Sorry. Okay, so the assumptions for performing a hypothesis test for mu, or the mean, when you do not know the population standard deviation, it is the following. Is the random sample, is it a simple random sample? And then the sample size has to be large, greater than 30, or approximately normal. The population is approximately normal. Okay, so in this case, we have a simple random sample and the sample size is large. Remember that it's over here. We found by reading that x bar is 2.2, s is 6.1, and n is 76. So the alternative hypothesis is, like we said, or the alternate hypothesis is that mu is greater than 0. So then the null is the boring one. There is no change that it's equal to 0. Calculating the test statistic with the formula, this formula here, we have that t is equal to 3.144. When it's true, the test statistic has a student t distribution with 75 degrees of freedom. What kind of test is this? This is a greater than symbol, so this is a right-tailed test. So the p-value would be the area to the right here of t is equal to 3.144. So using technology, what that means is, if you have a TCDF function, calculator, and I can explain that, but we're going to find everything in a separate way, so there's really no point. But if you want to use that function, I can go ahead and show you. The exact p-value is 0.0012, right? 0.0012. Since p-value, so what was the level of significance? That was 0.05. So the p-value is less than 0.05. So what does that mean? We reject the null at this level of significance. So finally, we reject the null, we support the alternate hypothesis, which is that it's greater than. So we can conclude that the mean weight loss of people who adhere to this diet for 12 months is greater than 0. Okay? Now let's get into the TI-84 plus. The t-test is a function on the calculator that will perform a hypothesis test when you do not know the population standard deviation. So how do we get this? We go stat, and we highlight the test menu, If the raw sample data, so if you're given like the summary statistics, like in this case we were given X bar, S, N, so we would use the stats option, the stats option. But if it's raw data like a list, we would use data. So pretty straightforward. So let's show how to do it. Okay, so same situation. We have 76 subjects, N is 76. What else here? X bar is 2.2. Standard deviation S is 6.1. So you need to get nice and cozy with taking out the information when you're reading a paragraph here, okay? So you hit stat and then you highlight tests, select t-test, which is the second option, and then you enter in all this stuff here. Now the this 0 represents the null hypothesis value, right? So the null hypothesis was that mu is equal to 0, so this is our mu 0. So that's why you would enter 0 there. Then it's a right tail test. Right? So that's why, and it's greater than the mu 0, which was 0. And then you would just hit calculate, and there's all your info. You see you have, it even calculates the t statistic, the p-value, you know, which is 0.00112, 0.0012. And it's the same thing. We reject HO, so we conclude that the mean weight loss of people who adhere to this diet for 12 months is greater than 0. So let me show you on, I'm using my iPad, so I don't have the same interface that I usually do, but I'll quickly show you here. Where is it? There it is. How to do this. Okay, so stat. See how it's edit, calculate, tests. So you highlight tests. Then you go to t-test, okay? And then it's either data or stats. So see stats. Data tells you the list, you know, you need to have a list entered. But then summary stats are when you're given, you know, the initial value, 0. Then you have that X bar was 2.2. Okay. The sample standard deviation was 6.1. And the sample size was 76. Let's plug that in. And this is a right tail test, so we highlight the right tailed here and just hit calculate, and there it is. Okay, this app is like it's called, I think, Graphing Calculator or something, or GDOT Calculator, and I found it, and I have this is on the iPad, but you can also get it on the iPhone, obviously. Okay, great. Hope that was informative. Let's go back to where we were. Example 2, hypothesis test. Generic drugs are a lower cost substitute for brand name drugs. Before a generic drug can be sold in the United States, it must be tested and found to perform equivalently to the brand name product. The U.S. Food and Drug Administration is now supervising the testing of a new generic antifungal ointment. The brand name ointment is known to deliver a mean of 3.5 micrograms of active ingredient to each square centimeter of skin. As part of the testing, 7 subjects applied the ointment. 6 hours later, the amount of drug that has been absorbed onto the skin is measured. So this is the amount of drug that was absorbed. So they give us a list. So how strong is the evidence that the mean amount absorbed differs from 3.5 micrograms? So right away, what do we have here? We have mu is 3.5, right? That's the null hypothesis. Okay, the alternative hypothesis, or H1, you know, they use H1, sorry, just to be consistent. How do we know what that is? It tells us here the mean amount is or differs from, so it's different. So differs, different, you know, that kind of thing, just means does not equal. So mu does not equal 3.5. Alpha is 0.01, that's important. And we have 7 subjects, and this is our data. So we're gonna need to enter this into a list. Okay, so let's go ahead and do that. So, oh, we need to check the conditions, right? The assumptions. So it's small. Because it's small, it's only 7 points. We have to check that the population is approximately normal. So a good way to do that is create a dot plot. There's no strong skewness and no outliers, so we can keep going. And again, here's the null and the alternative hypotheses, or the alternate hypotheses. I know I'm going to keep saying alternative because I'm teaching another class in which it's named alternative, but alternative are used interchangeably. So I just want to make sure that none of you are confused by my usage of that word. Okay, so the first thing we need to do is enter the data into a list. Okay, so let me go ahead and show you how to do that part first, right? So how do we enter this? We have to go to stat. Then you hit the thing edit, and then you enter the numbers. But I'll show you with my graphing calculator here, okay? So open up your calculator, have it handy. Let's do this together if we can. Okay, so here's a calculator, stat, and then it's on test right now, but click on edit. Then hit edit. See, that's my L1 right there. So on L1, I'm going to enter the data 2.6. 3.2, 2.1, 3.0, 3.1, 2.9, and 3.7. And there's still more. Oh, no, okay, let's delete that. So yeah, 3.7. So there's 7. There it is. So just again, how did I get to this list right here? I hit stat. Make sure that the edit button is highlighted. Hit edit again, and there it is. It should come up. Okay, so now that we've done that, let's go ahead and run the test. Okay, so again, back to stat. But instead of edit being highlighted, we're going to go to tests, okay? And we're going to highlight t-test, okay? And we are not given stats, we're given data, so let's highlight data, okay? So our null hypothesis is that mu is equal to 3.5, so we got to enter that in there. And the list, okay, if that's fine, we got the list, that's L1, okay, so we're going to use what we've just entered. And then finally, we need to tell the calculator, frequency, we just leave it as 1 if you have one list. Remember, frequency means, do you have a frequency list attached to this data? Like, you know, do you have a list that tells me, oh, this occurred 2 times, this occurred 5 times. And since we don't, we just leave it as 1. Now, what kind of test is this? This was a does not equal, so it's a two-tailed. Okay, we hit 2 tails here, or does not equal. Then calculate, and there it is. You have your t statistic value, your p value, your x bar, s, and n. So it does all the summary statistics for you as well. So that's super nice, okay? So now that we have that, so just to recap, what did I do? Just really quickly, sorry. For those of you that are like, wait, what happened? I guess you could rewind. So stat, edit, enter my list. Sorry, I hit something wrong. So stat, edit, list. Then stat, tests, t-test, make sure data is highlighted, enter the initial mu, the list, frequency, and then does not equal, and then hit calculate, okay? So let's go ahead back to the problem. Okay, so that's kind of what we had here. The p-value is 0.0256. The level of significance was what? Here, 0.01, remember that? So alpha was 0.01. So we need to compare p-value to alpha. P-value is going to be greater than alpha, right? Because 0.0256 is greater than 0.01 today, okay? So since it's greater than, we do not reject the null at this level. So you can say fail to reject or do not reject. Okay, and so finally, what's our conclusion? We'll say there is not enough evidence to conclude that the mean amount of drug absorbed differs from 3.5 micrograms and possibly could be equal to 3.5. Okay. All right, here, now we're going to do the critical value method, which is a little different. Okay. So let's talk about this. Okay, so to test a hypothesis about a population mean when, sigma is unknown. Okay, let me go back. Sorry about that. Hello, go away, thing. How do I, oh wait, no, that's not what I wanted. I want to get away from, how do I, sorry about that. Okay, I did it again. Okay, so the critical value for a left tail test is denoted with the symbol T sub alpha, negative T sub alpha, and I'll show you what that means in the picture here. So if we have a picture, the left tail test will be to the left, and your value negative T alpha would be here, and then the shaded part is like right here. Okay, so that would be your critical value would be here, negative T sub alpha. Okay, now that's the left tail test, and we would reject it if T was somewhere in the pink, right? So if T is here in the pink. Okay, another way to think of it, probably more accurate, right, is if T is less, the value of T, the T statistic is less than that negative T alpha, then we would reject HO. Okay, the next one, right-tailed, is similar, okay, except that the value of T alpha is positive. Okay, so then the area would be to the right. Okay, so the critical value basically is like the, where the area starts, the shaded part. Okay, and if T is in here, then that, in other words, we would reject the null. Okay, so if T is greater than or equal to T sub alpha, we reject HO, or reject the null hypothesis, okay? And then finally, the two-tailed situation is pretty interesting because it's two tails, right? You have here, you have here. But instead of just having one critical value, you have two because you're going over, remember that this is, so this all has, the pink areas, and it has to be an area of size alpha. So this pink side is alpha over 2, and this is half of alpha because of symmetry. And therefore, together, they make the entire alpha. So here, what's the value here? That's negative T sub alpha over 2 right there. And this is positive T sub alpha over 2. So if the T is here in the pink or here, we would reject. So if T is greater than the positive T alpha over 2, then, or T is less than or equal to, greater than or equal to, negative T alpha over 2, we would reject. Then null, okay? Otherwise, we would fail to reject. Okay, let's look at this now, an example. A computer software vendor claims that a new version of their operating system will crash less than 6 times per year on average. A system administrator installs the operating system on a random sample of 41 computers. Okay, fine, 41 computers. Okay, at the end of the year, the sample mean number of crashes is 7.1 with the sample standard deviation of 3.6. Can you conclude that the vendor's claim is false? Okay, use alpha is equal to 0.05 significance level, or 5% significance level, okay? So let's see here. So let's check the assumptions. What are our assumptions? We have a simple random sample. Okay, check. And then the sample size has to be large. What's the sample size? So that's bigger than 30, so fine. So we can use this, okay? So what's the initial hypothesis, right? What's the claim? The claim is that the new version of their operating system will crash less than 6 times per year on average. Okay, so if we want to conclude that the vendor's claim is false, then we would have to consider that greater than or less than. So they chose greater than here. That's interesting. Okay, so can you conclude? So I know that sometimes we say less than. So if you had set it up like this, which is what the word less than seems to imply, that would be if you're just, can you prove his claim, right? But since we have to prove that the claim is false or conclude that the claim is false, that means that it has to be greater than. So what would make it false if our conclusion was that it was greater than 6 times per year, okay? Why don't we have an equality, somebody asks? Because the equality is always with the null hypothesis, not the alternate hypothesis. Okay, so we use a significance level of alpha is equal to 0.05, and then this table, A3. The degrees of freedom is 41 minus 1, which is 40, so there you go, right? Remember, degrees of freedom is n minus 1. This is a right tail test because of the greater than. So the critical value is this t value here with the area of 0.05 in the right tail, okay? So the critical value is 1.684. So T sub alpha is 1.684. So then from the problem, we have this, that X bar, we have the initial mu, we have S, we have N, and now to find the test statistic, meaning that we actually use these, we're going to plug X bar, mu sub 0, S, and N all into this equation right here. Okay, so here, this, and this goes into here, 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 and here. And that's what all this is. And you can put that in the calculator. If you enter this in the calculator, by the by, make sure you put parentheses here. You know, just to be thorough, I would do that. Sometimes you could get things wrong. Okay, fine. So it's 1.957. That's the critical, right? I mean, that's the t test statistic. So this is the t statistic. And then this one is the critical value. So somebody might ask, well, how do I know the difference and what? There's 2 t's. Well, the critical value, it comes from the chart, yeah? And the critical value is connected to the area in the right tail, and it's given by, that chart, and it's also dependent on your degrees of freedom. Okay, so that's apart from the problem itself. So the actual t statistic comes from the problem where you get the data and then you use the formula for t and then plug it in and then you find the value, and that's your t statistic, okay? So since it's in the critical region, what do? We reject, right? Because it's inside here, right? It's here. So we reject HO, that's our decision. And then finally, we can conclude that the mean number of crashes is greater than 6 per year. Okay. So again, finally, you should know the assumptions for hypothesis test for mu when sigma is not known, and then how to perform hypothesis test for mu when sigma is unknown using the p-value method, how to estimate a p-value from a table for 1 and 2 tail tests, and then how to perform hypothesis tests for mu when sigma is unknown, or the standard population standard deviation is unknown using the critical value method. Okay, and that's it for 9.3. There's your super fun homework. Good luck, happy studying, and I will see you in class.